All right, let's get right into it. We're going to talk about something that is quite literally the digital ear for our computers, the discrete Fourier transform. This is the magic behind so much of the tech we use every single day. Have you ever wondered how your phone can pick your voice out of a crowd? Or how a music app just knows what song you'd like next? Well, the answer isn't just code. It's about teaching computers how to listen. And to do that, they have to break down messy, complex signals like sound into their simplest, most basic ingredients. So here's our game plan for this explainer. First, we'll nail down the core idea. What even is Fourier analysis? Then we'll hit a major roadblock, the problem of infinity. After that, we'll meet our hero, the practical DFT, and its superpowered sidekick, the FFT. And finally, we'll peek behind the curtain to see what the DFT is really seeing. Okay, first things first, let's tackle the big idea, Fourier analysis. And you know what? At its heart, it's actually a pretty intuitive concept. I want you to imagine you just made a smoothie. It's got this complex, unique flavor, right? Well, Fourier analysis is like a machine that can taste that smoothie and tell you the exact recipe. Yep, that's 50% banana, 30% strawberry, and 20% spinach. It takes any complex wave, like a sound, and breaks it down into the simple, pure sine waves that it's made of. It's the ultimate recipe finder for signals. Now, in the pure world of mathematics, this idea is absolutely beautiful. But when we try to bring it into our messy, real world of digital computers, we hit a snag. A big one. See, the perfect ideal tool for the job is something called the discrete time Fourier transform, or DTFT. On paper, it's flawless for analyzing a signal that we've sampled. But it has what you might call a fatal flaw when it comes to actually using it on a computer. And here is the heart of the problem. The DTFT gives you a perfect, continuous, infinitely detailed answer. But a computer can't think in terms of infinity. It can't run an infinite number of calculations. It needs a clear start and a clear end. So this perfect tool is, for all practical purposes, impossible to compute. We hit a wall. So what do we do? How do we build a bridge between this beautiful, infinite mathematical idea and the finite, practical world of our computers? Well, this is where the discrete Fourier transform, the DFT, comes to the rescue. It makes a really smart, really practical trade-off. Instead of chasing that impossible, infinitely detailed spectrum, the DFT says, how about I just give you a handful of key data points instead? It gives us a discrete, finite spectrum, something a computer can actually work with. It's basically a simple contract. You give the DFT a finite chunk of your signal, let's call it n samples, and in return, it gives you back exactly n frequency components, or bins, to look at. It's a fair trade, a finite input for a finite, and most importantly, a useful output. And if you peek under the hood at the math, don't worry, we won't go deep, you can see why this works. That big E-looking symbol, sigma, just means add things up. And notice it has a clear start and a clear end, from n equals 0 to n minus 1. It's not trying to go on forever. This formula is built from the ground up to be something a computer can actually solve. Okay, so the DFT was a genius idea. It made the impossible possible. But there is a huge catch. In its original form, it was slow, like painfully slow. It needed a superpower to be truly useful. Here was the issue. Its computational complexity. To analyze a signal with n points, it took roughly n squared operations. Now, what does that mean? It means if your signal gets twice as long, the calculation takes 4 times as long. If it gets 10 times longer, it takes 100 times longer. For real-time applications, that's an absolute deal breaker. And then, in the 1960s, everything changed. A ridiculously clever algorithm called the fast Fourier transform, or FFT, was developed. It found a way to get the exact same answer as the DFT, but just way, way faster. For a decent-sized signal of about 4,000 samples, we're talking 300 times faster. Unbelievable. And this table right here shows you just how big a leap that was. Going from n squared down to n log n. That isn't just an improvement. That's the difference between a cool idea that's stuck in a lab and a revolutionary tool that can power the entire digital world. And look, don't just take my word for it. This quote from MIT OpenCourseware says it all. The invention of the FFT is maybe the single biggest reason that modern digital signal processing even exists. It unlocked everything from our cell phones to medical imaging. It was a total revolution. All right, we're on to our final section. Because to make all of this finite magic work, the DFT has to make one last, very important, and honestly kind of weird, assumption about the world.
So, to handle this finite chunk of data you've given it, the DFT has to pretend something about your signal. It has to see it in a very specific way.
Here's the assumption. The DFT believes that the little piece of signal you gave it isn't just a one-off thing. It assumes it's one single cycle of a pattern that repeats itself forever and ever. It basically takes your signal, wraps it around in a circle, and connects the end right back to the beginning to create an infinite loop. Now, you might be thinking, okay, that's weird, but so what? Well, it matters a ton. This circular assumption is the root cause of common headaches in signal processing like aliasing and spectral leakage. It's also why you hear about things like cyclic convolution. It all comes back to this core assumption. If you don't understand that the DFT thinks the world is a repeating loop, you can't possibly interpret its results correctly.
So that really leaves us with a fascinating thought, right? The next time you ask your phone a question or listen to a song, just remember the incredibly clever compromise happening deep inside. That device is taking our messy, complex, and potentially infinite world and pretending it's a simple, finite, repeating circle. Also, it can break it down and understand what's really going on. It's a beautiful, practical lie that makes our digital world work.